which is Professor Zhigang Xu from Chang'an University, who is managing a very large field experiment for the university, and that's one of the leading experimental field in China for connected automated vehicles. Okay, Zhigang, the floor is yours.
Okay, thank you.
Yeah, can you share the screen with us?
Okay. Hello, can you see my screen?
Yes, yes, we can.
Yes, okay, thank you. Hello, everyone. Today, my presentation is a precise fuel consumption prediction model using LSTM, deep networking for eco-driving. Okay. Tonight, I will give my talk from the following 5 aspects. The first one is motivation. The second is problem statements. And the third is optimal configuration of LSTM-based FuelNet model. And then I will give 2 use case for our models, and then I give my conclusion. First, the motivation. Now, the transportation emission is a significant and a growing contributor to particulate air pollution. And oral fuel consumption can be measured directly in real time by instruments, but fuel consumption prediction for any future trajectories can guide drivers make the optimal driving strategy based on energy efficiency. So FCP, fuel consumption prediction, is also used to solve a series of intelligent transport-based issues, such as optimization of intersection traffic, smart lane changing, and for autonomous vehicle and remaining managing prediction, such as like Chaoru and the first speaker. Yeah, we need predict how many remaining manage for charging or for the for fuel. Okay. I will talk about some thing about LTSM. LTSM is a okay. LTSM is a variant of RNN, and which has a single tangent layer and only has short-term memory only to the Washington gradients problem. And LTSM is a dedicated deep learning network for time series training and identification, which can well solve the vanishing grades problem in processing long-term dependency information that are deep learning models. LTSM is very good for predicting for the data with the 1D data, such as the fuel consumption, trajectory, and time series. Okay, here we will talk about what's our problem. Here we can see a figure. There are 3 different trajectory. First one is Y1. This is trajectory with a high speed. And the second Y2 is the trajectory with the stop-go trajectories. And the last one is optimal trajectory. You can see this is an intersection. We first, for the first scenarios, we drive with high speed and try our best to go through the intersection. The second one is we stop on the stop line and wait for the red lights and then go through the intersection. The last one is the optimal trajectory with the optimal speed. Then we, without any stops, we can go through the intersection. And for the eco-driving, for an autonomous vehicle, the computer can generate many trajectories, but for each trajectories with different fuel consumption. So which one is best? If we can predict the fuel consumption for each one, so we can select the best trajectory. Okay. This is the structure of the LSTM. It includes 4 gates: the 4 gates, input gates, cell gates, output gates. This is a very famous deep learning network, and it is a very with a very simple structure. The first, this network is used to the voice recognition and for the text recognition, but few people use this network to predict the fuel consumption. Okay. There are many forms for the LSTM, such as with one history data to predict many, and many data from the history to predict one, many to many, and with the shift of the many to many. This is the history, this is the future. So we use this form, many to many, without any shift. Then we use the input data from the vehicle, such as the velocity and the acceleration and the GPS and etc. Then we screen which inputs cumulation is the best one. Cumulation is best one. So we do many experiments to screen this input. You can everyone can see this is the fuel consumption for trajectory. This is the speed of the trajectory. This is the acceleration. This is latitude. This is longitude. And we make a different combination of speeds plus GPS plus acceleration. And the second is GPS plus acceleration. And the third is GPS plus speed. The fourth is speed, and the last one is speed plus acceleration. Okay, you can see the prediction result. This is the first one. We can see this solid line is the actual fuel consumption, and the dot line is the prediction. Both cover very well, and this is the error, absolute error, and this is the input with GPS and acceleration. This is GPS with speed, and the D is speed. The last one is acceleration and with the speed. You can see For the last case, the relative error is very small, very small. And we use the RMSE and RE and R square as the metrics for evaluation the prediction of the fuel consumption. Everyone can see a very interesting result. You can see we do the experiments with eight speeds. The first one is 10 kilometers per hour. The second is 20 kilometers per hour. Third is 30 kilometers per hour. And the last one is 80 kilometers per hour. You can see for the lower speeds on 10 kilometers per hour and 20 kilometers per hour, the accumulation of speed, that means we only use the speed, we will have the best performance. This is the prediction. This is the error. This is the R square. You can see with the smaller speeds, we only use speed can achieve the best performance. But for the speed up larger than 30 kilometers to 80 kilometers per hour, the combination of speed plus acceleration achieve the best performance. We can also see that at the high speed, we get the best performance. That means 98.3%. So this is the interesting result from the experiment. And then we analyze the data. We found maybe the main factor achieve this result is because at the lower speed, like 10 kilometers per hour and 20 kilometers per hour, the measurement of acceleration is not good. We know the measurement instruments for measurement of acceleration play well on high speed, on the low speed, or on the stationary status. The sensors of the acceleration will produce many noise on the lower speeder. This is the main factor lead this result. Okay. So when we found the best combination is the speed plus acceleration, then we will optimize the LTSM network. First is the training size, and the second one is the batch size. Training size is the size of the training pool. How many data we use to train our deep learning network. And this batch size, that means for each time of the prediction, we use how many samples to predict the fuel consumption. And then we get the best size is 200, and the best training size is 20,000. Okay. Then we, after many hyperparameters experiments, we get the optimal parameters such as the batch size, the number of iteration and the hidden size, and the optimization function is Adam, and the loss function is MAE. So we concrete this network for the for the prediction of the actual data. We conduct two experiments. The first, we compare the performance of the FuelNet. Or here we proposed an other networks like the traditional GRNN and RNN and GRU, the traditional networks, and also the physical model like a VSP and a VT macro. This is the physical based the model. We can see that FuelNet play well. You can see it is far better than our traditional models like the VSP and the VT macro and our network. The RNN is also a deep learning network, but FuelNet is also better than RNN. We can see the result. Yeah, this is the error, the relative error. The relative error concentrate on a very small channel. So, but for our models, the error distribution has a long real distribution. But here for the FuelNet, we focus on 0 to 0.1. So this network is has a very good performance. Okay. This is for the low speed from 10 to 30 kilometers per hour, and this for 30 to 6 kilometers per hour. The FuelNet is very close to the actual data. You can see FuelNet perform very well. And this for the 60 to 90 kilometer per hour, and the R square is 97.5, and we have two use case. First one is the passing the intersection. We do this experiment in China University connective and automated vehicle test site. For each scenario, this is the high speed scenario. This is the optimal speed, and this is the stop and go. For each scenario, we have 3 experiments, and then we do this experiment in China University CLV test site, and this is the intersection. So from the data, we can see that for the optimal speed, this is the start, and this is the cruising status, and you can see the speed can keep constant, and the fuel consumption is very low. It's very low here. Yeah. And this is high speed. This is high speed. The speed increase, increase, and the fuel consumption also increase with the speed. And we repeat this. This is the stop go, stop go, stop go. When the vehicle stop here, and is also cause some big fuel consumption like this. We repeat this experiment for 3 times. The results are very same. You can see
It seems that the internet of Professor Zhigang Xu isn't too good. Zhigang, can you still hear us? Okay, we couldn't hear you. Probably, probably we will have 10 minutes break for the coffee break, and we will be back at 1:20, and Professor Xu will finish up his presentation, and we will have Q&A session with Professor Xu, and after Professor Xu's presentation, we have another 2 speakers, and one is Professor Xiaopeng Li from University of South Florida, and the other one is our first speaker, Professor Yiming Bie from Jilin University. Okay, so we have 10 minutes coffee break now, and after that, your Professor Xu will finish up his presentation, and we will have Q&A session with him. Okay. And we will continue at 1:20.
Okay, I will continue my presentation. Okay.
Okay, sure.
So the first experiment we conduct in the CV test site of China University. We test 3 scenarios. First one is with the optimal speed, and the second one is with high speed. The last one is with the stop go. You can see these three scenarios, and this is the CV test site of China University. This is the vehicle we used to conduct the fuel consumption experiment. So from this table, we can see that with the optimal speed, we have the lowest fuel consumption. This is the predicted value, and this is actual value. The predicted value is very close to the actual value. So this can be used to evaluate different trajectories generate from the algorithm such as the lane change and emerging and many scenarios. We can generate different trajectory. So we can use our network to predict what's the fuel consumption if we use this trajectory. It's very is far better than the physical based models such as WSP and WT Macro. This is the high speed. We know with the high speed, the oil pump will start, so it will consume more fuel. Okay, this is the this is the second use case. From the data of a truck of Shanxi Motor Group, we use our model to monitor the fuel consumption. From the history data, we find from the 402nd second, there is a jump. There is a jump of the fuel consumption, the gap of the actual value and the predict value. There is a jump, the error. There's a jump of the error. So we analyze this data. We find from the recording log, we find that in this scenario, the vehicle get some fault. The pipe of the engine is broken. So the driver record this phenomena, and then we can use the model to find this fault. Okay. So I will give the conclusion. For this model, the best input combination is speed plus acceleration, and use the FuelNet model can accurately predict fuel consumption in wide speed range from 10 to 80 kilometers. And compared to traditional models, LSTM-based model perform best. And it can also conclude that from two case study that the FuelNet model is suitable for different driving trajectory to predict fuel consumption, which can provide a reference for selecting driving behaviors that can save energy and reduce emission. And it can also monitor the fuel consumption of the trucks. Okay, that's all. Thank you very much. Thank you for your attention.
Thank you, Zhigang, for your presentation. And the performance is indeed quite good. And for regarding your model, any questions? In the interest of time, probably we can only accommodate 2 questions, and then we will proceed to the last 2 presentations by Professor Xiaopeng Li and Yiming Bie. Okay, any question for Professor Zhigang Xu?
I have a question, Professor Xu. Thank you. Thank you for your presentation. My question is why we need to say the performance as the different speed range. So I think when you speak the speed, it means the speed at the only at the second is the instant speed or the average speed when you divide the speed groups.
Oh, in fact, many models are sensitive with the speed. For example, for the VSP and the weighted macro, and we publish a paper, in computer-aided civil and civil engineering, civil and infrastructure engineering. We find for the VSP and weighted macro, like these physical-based models, they are sensitive to the speed. Is generally for the high speed, the prediction performance is better than the low, because when the vehicle drives slowly, there are many other factors like the electronicals and friction and the wind, especially such as the air conditioning. This will achieve more for the fuel consumption. So the arrow is bigger. But for the high speed, these factors can be omitted because most of the energy is used for drive the vehicle. So for the traditional physical-based models, they have different performance. But for our proposed FuelNet, this is not a problem because it used the history data, especially long series of the time series data, so it can perform better. I think this is the problem. Okay.
Follows the question. So I say the speed is also an input variable. So do you think will it influence the final results? I mean, it is also input, but it is also a group creating a ruler. Does the inputs and the final results has the relationship? I mean,
for example.
For example, when you say the performance for the 60 or 90 minutes, 90 kilometer is the best. Yeah. So it means your input is only consider the trip, whose speed is ranging from 60 to 90, or consider also consider other speed less than 60 when you just try to predict the consumption for the 60 to 90?
I think for the 60 to 90, the speed and acceleration will be the main factor for the fuel consumption. So the noise is the noise is not the main factor. This my assumption. Okay.
Professor Xu, for your experiments, you are using constant speed of 70, 80, 60,
yeah,
50. Yeah. You are using speed, right?
Yeah, for this, for the optimal is very like the constant speed. For is a cruising status. You can see, yeah, because this an autonomous vehicle, we can control the speed with the algorithm, so it can achieve constant speed accurately.
Okay, I see. Thank you.
Yeah.
Thank you. We can communicate offline. I think we have many questions needed to be discussed. Okay, thank you.
Probably one last question for Professor Xu, and then we can proceed for the for the next speaker.
So, Dr. Xu, this is Xiaopeng Li.
Okay. Hi, Xiaopeng.
Morning. Good evening, actually. So how did you do the optimization? And is that a local optimum or it's the global optimum?
Oh, okay. We use the VSP as the mathematical objective. So we use the solver of MATLAB to get the optimization of the trajectory. Then we apply this trajectory for the experiment. So yeah, we have published one paper on IEEE ITS. I use that solution. Okay.
Is that local optimal or global optimal?
Global.
Okay, yeah. Thank you.